So here are some basic properties that result from the dot product. Can you see that it doesn't matter which way you do the dot product? That u dot v would be the same as v dot u, because you're just multiplying the components together and adding them. And if you would do that in a different order, it wouldn't matter. If you have another scalar out in front times by a dot product, you can do the dot product first and then multiply. Or you could multiply first and then do the dot product. And it will have the same result. And the dot product is distributive. You could add your vectors together first, or you could do the dot product with them separately and then add them together. And if you do the dot product with the zero vector, if one vector is all zeros, it should make sense that when you add up all those zeros, you will still get 0. And so that works as well. Yes? Can you take a vector with a power of 0? I don't know if vectors with a power of 0. I don't know if it makes sense to do that. See, now you're thinking multiplication and dot product. This is dot product, which is different than multiplication. Now, with these are, I would call, the boring properties. Now we can get to the exciting, interesting results. A isn't that interesting. But the dot product of a vector times by itself is the same thing as its length squared. Okay? So, for example, if you have 1, 3, 2, and you do the dot product with 1, 3, 2, can you see that you're going to get 1 squared plus 3 squared plus 2 squared? Which, if this was in a square root sign, would be the length of that vector. But it's not in the square root sign, so we say that it's its length squared. And here is the most important result. The dot product of two vectors is the same thing if you took both the lengths of those vectors and multiplied them together, and then multiplied by cos of the angle in between. Now, the reason this is so important is because now we can quite easily, let's say I have the point 2, 4, and I have another point over here, 3, 1. I can make those both position vectors. We can now find that angle really quickly and really easily. If you had to use your previous knowledge for how to find it, what would you do? How do you find that angle? Make a triangle. So here we've got like this. And then you could use your distance formula and find that length. And your distance formula and find that length. And your distance formula and find that length. And then you could use the cosine law to figure it out. Well, the vectors, that can get replaced by this, which is a little bit quicker. You still have a distance formula built in for two of them. But instead of having to find the distance formula for the third one and then apply the cosine law, we can just do the dot product and use that result to solve. Yes?
So but we know like divide u times v by by that, and then takes the inverse of cos gets angle.
Yes. Yeah. Now, based on this result, right, if you have two vectors that are perpendicular, and here is a new word for perpendicular. Have you heard of the word orthogonal before? Since cos of 90 degrees is 0, anytime you have your dot product equal 0, you already know that those two vectors are at 90 degrees. Because if you look back at this previous result here, if this is equal to 0, then this side has to equal 0. And as long as one of your vectors isn't a 0 vector, right, and if you have something that's a 0 vector, there won't be any angle between it and something else anyways. But then you would know that your two vectors are 90 degrees to each other. Since cos is greater than 0 for any angle between 0 and 90 degrees, but cos is less than 0 between 90 and 180, right, according to your cast rule and those kind of things. If your dot product is bigger than 0, you know that your angle is between 0 and 90. If your dot product is less than 0, then you know that your angle is obtuse. And if two vectors are parallel, then the dot product will just equal the lengths of the two vectors times by each other, because cos of 0 degrees is going to equal 1. And you can rearrange that formula that we had before, and we get a formula for cos theta based on the dot product of two vectors, or the scalar product, divided by both of its lengths.